In this presentation, we will discuss the bearing capacity and settlement of a pile foundation. In shallow foundations we see that the depth dF is less than the breadth b. It is opposite in deep foundations such as piles, where the depth is often much greater than the breadth. In a pile, the depth is the same as the pile length L, and the breadth is the pile width or diameter, denoted by d. If we have a 400 kN column load, a simple pad footing is sufficient to carry the load. For a larger 800 kN, a pile may be more suitable, depending on the soil conditions. For a much larger load of say 2500 kN, we have to go for a large diameter pile such as a pier or caisson, or a pile group consisting of more than one pile. The figure on the right shows a 2x3 pile group. A reinforced concrete pile cap at the top is used to rigidly connect the pile group to the column. These days, we are seeing more and more super tall buildings, which are buildings taller than 300 meters. They can have column loads as high as 40,000 kilonewtons. None of the foundation types we discussed so far would work. Here, we use piled rafts and arborettes. Piled rafts are large rafts on top of several piles. We take advantage of both the raft and the piles. Raft helps with the bearing capacity and piles help reducing settlements. You can think of piled raft as a larger version of a pile group with a pile cap at the top. Barrettes are deep trenches filled with reinforced concrete. In plan view, they can look like a large I, X, T, H, L, or Y. When a load Q is applied to the pile head at the top, part of it is carried by the shaft and the rest is carried by the pile tip. For equilibrium, Q equals Qs plus Qt. Two common ways of installing a pile in the ground are by driving or casting it in place. The first is called a driven pile. The second is called a cast-in-place pile or board pile. There are also other types of installation such as vibratory driving or jetting. Driven piles are hammered into the ground by a pile driving hammer hitting the pile head repeatedly. For board piles, we dig a hole in the ground, place a reinforcement cage and fill with concrete. Vibratory driving is effective in granular soils, where the pile driven using a vibratory load. Jetted piles are installed using a water jet to loosen the soil at the pile tip. Piles are generally made of timber, steel, or concrete. Timber piles have been used centuries ago. Tree trunks are used as piles with natural taper. Their lengths can be limited and may require splicing. Their load carrying capacity is relatively low, in the order of 500 kilonewtons. Steel piles are generally in the form of I-sections or pipes driven into the ground. Concrete piles can be precast or cast in place. Both steel and concrete piles have higher load carrying capacities. Sometimes, we also use composite piles that are made of two materials, taking advantage of both. For example, a steel pipe pile can be filled with concrete, or the head of a timber pile can be covered with concrete at the water level to protect the timber from fluctuating water table. When the soil near the surface is very weak, with a stiff stratum lying not so deep, it is prudent to transfer the entire load to the pile tip, without relying on the pile shaft to carry any load. Here the pile tip rests within the stiff stratum. Such piles are called end-bearing piles, where QS equals 0. When the load applied at the head is mainly taken by the pile shaft, it is called a friction pile, where QT equals 0. These two are the extreme cases. Very often, we are between the two, where the loads are carried both by the shaft and the tip. Depending on the extent of displacement of the soil around the piles are called no, low, or high displacement piles. A bored pile does not displace the soil laterally and hence is a no displacement pile. In the case of driven piles, larger the diameter, higher is the lateral displacement of the soil near the pile. The photograph on the left shows a 2x5 pile group made of 10 driven concrete piles. The photograph on the right shows a 2x2 pile group with the reinforcement in place for the pile cap to be cast over the piles. The photograph on the left shows some treated timber piles that have been driven into the ground. The photograph on the right shows a group of batter piles, also called raked piles. They are driven at an angle to resist lateral loads. The photograph on the left shows a hole made through rock for an end-bearing cast-in-place pile. The photograph on the right shows the reinforcement cage being placed within the hole for a 3-meter diameter cast-in-place pile. A steel casing is also used for the top few meters to prevent soil from the walls of the excavation getting into the hole. These two photographs are taken from construction sites, one in Kuala Lumpur, Malaysia, and the other from Townsville, Australia. The left shows a bored pile construction site and the right shows pile driving. The photograph on the left shows some octagonal precast concrete piles ready for driving. The bottom ends are pointed to facilitate driving. The photograph on the right shows the same piles driven into the ground, forming a pile group to carry an overhead bridge. Here are some steel piles in the form of H-sections that have been driven into the ground. We can list several applications of deep foundations. The first one here shows a situation where there is weak soil to a limited depth, underlain by a stiff stratum such as bedrock. We have here an end-bearing pile such that the entire column load is transferred to the stiff stratum, without stressing the weak soil. The second application shows a heavy column load which may be too much for a pad footing. A pile works better here. The third application shows under-reamed piles, used to resist uplift in a pump house. Under-reamed piles are cast-in-place concrete piles where the base is enlarged. They provide an anchoring effect. The fourth application shows raked piles used for resisting lateral loads. Piles are also used in underpinning of old foundations. The column load Q applied on the pile head is carried by the shaft and the tip. Therefore, Q equals QS plus QT. When the shaft and the tip loads are fully mobilized, they are QS ultimate and QT ultimate, respectively. Therefore, the ultimate load carrying capacity of the pile is Q ultimate, which is the sum of the ultimate load carrying capacities of the shaft and the tip. We divide this by a factor of safety in the range of 2 to 3, to arrive at the allowable load that can be safely allowed on the pile head. We have to calculate the ultimate shaft and the tip loads separately and add them up for the ultimate load for the pile head. For the shaft load, we are looking the equilibrium of a disc element and integrating it over the pile length. Fs is the skin friction per unit area, and P is the perimeter. The tip load is computed by multiplying the ultimate bearing capacity at the pile tip by the tip area. You can see that we must note two things here: A, skin friction Fs, and B, the ultimate bearing capacity at the pile tip. The pile load QZ acting on the cross-section of the pile and the skin friction Fs, vary along the pile length. They depend on each other. Here, again we look at the equilibrium of a disc element, to develop a relationship between the pile load QZ and the skin friction Fs. The two expressions we derived in the last slide and shown here on the left. We use them as the basis to infer Fs from QZ or the other way around. Here, we have shown 4 cases where we can do this. Spend some time here and understand how we deduce these variations. The plot here shows how the shaft and tip load develop with the pile settlement. Let's assume the pile is incompressible for now. For the first few millimeters of settlement, most of the load is taken by the shaft, with a very small fraction transferred to the tip. When the settlement is about 0.5 to 1% of the pile diameter, the shaft load is fully mobilized. From then, all the additional load on the pile head is transferred to the pile tip. When the tip load is fully mobilized, the settlement is in the order of 10% of the pile diameter. The take-home message from here is that the shaft load is mobilized well before the tip load. In this section, we will discuss the methods to calculate the load carrying capacity of the pile by adding the ultimate loads at the pile shaft and the pile tip. The horizontal effective stress sigma H dash is given by Ks times sigma V dash. Remember, we have used K naught, Ka, and Kp. This Ks is similar, reflecting how the soil is displaced laterally. The skin friction Fs per unit area is then sigma H dash times tan delta. Here, tan delta is the friction coefficient at the pile soil interface. Once we have the values of Ks and delta, we can find the ultimate shaft load. Here is the method suggested by Coyle and Costello, 1981, to compute the ultimate shaft load. Use the graph to find Ks. Delta is assumed as 0.8 times the friction angle. They suggested using the average effective overburden, computed at mid-length of the pile, for deriving the ultimate shaft load. Here are some suggestions for selecting the values of Ks and delta. Ks and delta are combined into a single term Ks tan delta, which is known as beta coefficient. The beta values suggested by the Canadian Foundation Engineering Manual, for driven and bored piles, are given here. It can be seen that the beta value of a bored pile is about 50% of that of a driven pile of same diameter in the same granular soil. Right next to a driven pile in granular soils, the effective vertical stress does not increase linearly forever with depth. It increases linearly near the surface and reaches a limiting value at critical depth denoted by dc. Beyond this depth, the effective vertical stress remains a constant. The ultimate tip load of a pile is the product of the ultimate bearing capacity at the pile tip and the cross-sectional area of the pile. Therefore, we need to know the ultimate bearing capacity at the pile tip. Let's compare the circular footing and the pile as shown in the figure. The depth df of the footing is similar to the pile length L, and the diameter of the footing B is similar to the pile diameter D. If we use the bearing capacity equation for a circular footing, we can deduce that the ultimate bearing capacity of the pile tip is simply the product of the effective vertical stress at the pile tip and a bearing capacity factor NQ. The failure mechanism is different for shallow and deep foundations. Therefore, the bearing capacity factor NQ is different to the one we used for shallow foundations. As before, NQ is a function of the friction angle. Different values have been suggested by Terzaghi, Meyerhof, Berezoncev et al., and U.S. Army. The values suggested by Berezoncev et al. Are popular. NQ values suggested by the Canadian Foundation Engineering Manual, 2006, for driven piles and cast-in-place piles are given in the table. It can be seen that the values for cast-in-place piles are approximately half of those for the driven piles. The NQ values suggested by Coyle and Costello, 1981, for driven piles are given in graphical form. Here are expressions for the skin friction per unit area Fs, and the ultimate bearing capacity at the pile tip in terms of penetration resistance. There are alpha method, beta method, and lambda method to determine the ultimate shaft load of a pile in clay. Here, we are discussing only the alpha method where undrained conditions are assumed. The adhesion along the shaft is the product of an adhesion factor alpha and the undrained cohesion Cu. Alpha varies in the range of 0.3 to 1.0, where the stiff clays and heavily over-consolidated clays are at the lower end of the range. For soft clays and normally consolidated clays, alpha is close to 1. Assuming undrained conditions, the friction angle in terms of total stresses is 0. Therefore NQ equals 1 and N gamma equals 0. The net ultimate bearing capacity at the pile tip is the product of the bearing capacity factor NC and the undrained cohesion Cu. What do we use for NC? From the work of Skempton, 1951, for piles where the length to diameter ratio is larger than 5, NC must be taken as 9. That means, for piles and clays, we will always take NC as 9. In this section, we will look at pile driving, a popular method to install piles in the ground. We use pile driving hammer to repeatedly hit the pile head and drive the tip further and further into the ground. The first here is a drop hammer, one of the oldest pile driving hammers. A heavy weight is lifted using a pulley or a hoist and dropped on the pile head. The second is an air or steam hammer, where air or steam is used to push the weight up and the drop can be free fall in single-acting hammers or assisted by air or steam in double-acting hammers. The third is a vibratory pile driver, where rotating eccentric misses provide a vertical sinusoidal force. On the right, we have shown the components of a standard pile driving hammer. The pile cushion is to protect the pile and the hammer cushion protects the hammer. The helmet holds the pile in position and aligned to receive the hammer blow. You have to select the right hammer. Typically, you would select the ram weight to be 25% to 200% of the pile weight, and to be 2% of the ultimate load carrying capacity of the pile. The table here lists some hammers and their energy ratings. Some of the pile driving hammer manufacturers are Delmag, MKT, Vulcan, Mitsubishi, Gobelco, BSP, Junton, Conmaco, ICE, and Meng. Pile Driving Analyzer or PDA, is a fairly modern device that can determine the load carrying capacity of the pile. The pile is instrumented using accelerometers and strain gauges, and a pulse generated during the impact is studied. PDA is not as reliable as a proper static pile load test but is a lot cheaper. In the photograph, you can see the cables running between the pile and the PDA. Pile driving formulas provide a crude way of estimating pile load capacity. Here, we equate the work done by the pile to the energy delivered to the pile head. Here, S is the set, which is the penetration of the pile tip per hammer blow. There are more than 10 different pile driving formulas. Due to their poor reliability, we use a very large factor of safety, sometimes as high as 6. The product of the ram weight and the drop height is the energy rating of a simple single-acting hammer. N is the coefficient of restitution, which is a measure of how much the hammer bounces off the pile, after the blow. We made so many assumptions and approximations in determining the pile capacity. How reliable is our estimate? Proof of the pudding is in the eating. Nothing like testing a pile for real, which is what we do in a pile load test. A proper pile load test can be very expensive. Still, there is no better way to verify our calculations. There are 2 ways of applying the pile load. The first one shown on the left consists of what is known as Kent ledge, consisting of heavy weights, for pushing down the horizontal reaction beam and holding it in place. In the second one, on the right, we use 2 reaction piles on either side of the test pile to hold the reaction beam. In both cases, a hydraulic jack is placed between the pile head and the reaction beam, and the pile load is applied in steps and the settlement of the pile head is measured at every load. Here, on the left you can see a pile load test being done using Kent ledge. On the right, the pile load is applied using 2 reaction piles connecting the horizontal reaction beam. Since the pile itself shortens due to the load it carries, the settlement of the head is greater than that of the tip. The head settlement is the gross settlement, which is what we measure on top of the pile head. The tip settlement is the net settlement, derived from the gross by subtracting the elastic shortening of the pile. Here, in a static pile load test, the pile load is increased in steps and the corresponding settlement of the head is measured using a dial gauge sitting on top of the pile head. The plot of load against the dial gauge reading is shown on the left for loading and unloading paths. During unloading, elastic rebound occurs, which gives the elastic shortening of the pile as shown in the figure as SE. Subtracting this from the dial gauge reading during the loading gives the net settlement, which is the settlement of the pile tip. Thus, we are able to derive the load versus net settlement plot. Here, we have the two load versus settlement plots, gross on the left and net on the right. Which one do we use for determining the ultimate load carrying capacity of the pile? Gross is simpler and is used by the most. Net is more rational since it is related to the bearing capacity failure and is preferred by the U.S. Army. Most standards or codes define the ultimate pile load as the one that corresponds to pile head settlement of a 25 mm, b 10% of the pile diameter, or c, QL on AE plus D on 30. De Beer, 1968, suggested having the load and the gross settlement both in logarithmic scale, which makes the plot bilinear consisting of two straight lines, with a well-defined ultimate load as shown in the figure. Davison, 1973, suggested that the ultimate pile load is where the settlement in millimeter is 4 plus D on 120 plus QL on AE. Here, D is the pile diameter in m. L is the pile length, A is the cross-sectional area and E is the Young's modulus of the pile. How do we locate this point on the plot? Well, mark 4 plus D on 20 on the vertical gross settlement axis. Draw a line from here, such that the slope is 1 vertical to AE on L horizontal. The point where the line intersects the settlement plot defines the ultimate load. U.S. Army suggests deriving the ultimate pile load using the net settlements by 3 different methods and averaging the 3. The first one defines the ultimate load as the one corresponding to 6 mm of settlement. The second one is the double tangent method, where the tangents are drawn initial and final segments of the curve, where the intersection defines the ultimate load. The third method suggests locating the point where the tangent has a slope of 0.0254 mm per kilonewton. Settlement of a pile foundations is relatively smaller than that of a footing. However, it still needs to be determined. Here is a simple method suggested by Poulos and Davis, 1974, using elastic analysis. The charts provided can be used to estimate the settlement of an incompressible pile. Here, I rho is the influence factor which depends on the Poisson's ratio, L on D, and H on L. H is the depth of the soil bed, which is assumed to be underlain by a stiff stratum. Es is the Young's modulus of the soil, treating as a linear elastic medium. Now that we computed the settlement of the incompressible pile, we have to add the elastic shortening determined using the actual Young's modulus of the pile EP. Thus, we accept that the pile does undergo elastic shortening. Vesics, 1977, method is based on elastic analysis too. He separated the settlement into three components S1, S2, and S3. S1 is the elastic shortening of the pile under working loads. S2 is the settlement due to the tip load, and S3 is the settlement due to the shaft load. In all three cases, the working loads are used. Here we use the standard equation from Hooke's law that settlement is equal to QL on AE. In place of Q, we use the tip load and only a fraction of the shaft load. The fraction depends on how the skin friction is distributed along the pile. For S2 and also for S3, in addition to the expression obtained from the elastic analysis, we can also use an empirical equation which sometimes gives a better prediction.